Over 2,000 years ago, the Roman philosopher Lucretius stated, "Nothing in the universe is unique and alone, and therefore in other regions there must be other earths inhabited by different tribes of men and breeds of beasts." In much the same spirit, today, man looks inquisitively into the night sky and wonders, are we alone?
Is there intelligent life outside the Earth? What is the Drake equation? And will we ever become a Type 3 civilization? All these questions will be discussed today. Okay, let's define the 3 questions we presented. Real quickly, although it's hard enough to just define life, we today will define intelligent life as life that is more intelligent or equal to human intelligence. For the Drake equation, it is a 1961 equation developed by Dr. Frank Drake that equates the number of intelligent civilizations within our galaxy that can possibly communicate with Earth with the product of 7 predictors. We will discuss those predictors later. A Type 3 civilization is defined as a civilization that can control energy at the scale of its entire host galaxy, as defined by the Kardashev's scale. At present, we are currently working toward a Type 1 civilization where we can use and store all the energy available on our individual planet. While we're at it, be sure to blast comments below with thoughts about the existence of intelligent life in our universe and what you think. Do you believe there is intelligent life other than ourselves in the universe? And if you do, attach a percentage to that belief. 100% would mean you're absolutely sure, and 50% would mean that there may or may not be intelligent life in the universe. Now, there are many schools of thought on this topic about intelligent life, and they range from 0% chance, believing we are the only intelligent life in the universe, to 100% chance and all percentages in between. The 0% camp has members with several different theories, but they all agree that we are unique in the universe. Many in this camp look at all the exceptional circumstances that had to happen just right for us to exist. They argue a hostile universe with radiation being prevalent to sterilize any chance of life and the daily cataclysms restricting the time needed for life to become intelligent, to form to an intelligent level, let's say. Many from this camp also cite the contradiction stated in the Fermi paradox, which concisely asserts that if these equations, such as Drake, are touting that there are heaps of intelligent life in the galaxy, then why haven't we seen them yet? Why have we not communicated with them? This camp tends to put the burden of proof on the camp that presumes intelligent life. One other victory the No Intelligent Life camp proclaimed was the WOW signal. In 1977, astronomers received a signal that was believed to be possible evidence of intelligent life. The astronomer on duty wrote next to the printout, "Wow!" exclamation point. For years after, astronomers searched the area of Sagittarius ambitiously to get another signal. Fast forward 40 years, and on June 7th, 2017, the WOW signal was explained. It was most likely generated by a comet, not intelligent life. The comet matched the WOW signal. The argument of the alone camp, in general, in one way could be summed up as, just because you don't want to be alone in the universe doesn't mean we aren't alone. On the other end of the spectrum, you have the 100% club. They tend to think that a statement such as, "we are unique," is rather arrogant and simplistic. They recall the Dark Ages and men like Tycho Brahe bending over backwards to adjust complicated mathematical formulas to support the idea that the Earth was the center of the universe. This club states in a vast universe, they find it very hard to believe that we are alone, especially with the enormous amount of stars in the Milky Way alone. They tend to believe that nature, with the ingredient of time, will ultimately spring up life in multiple places. They defend against the Fermi paradox by saying our ability to reach out or discover life outside our solar system with our primitive instruments is very feeble in technology's early stages. A small fraction of people even subscribe to a zoo theory, which in general states that intelligent life has the ability to hide itself from our instruments while they observe us like zoo animals. Additional arguments stress that scientists can't even agree on the definition of life in general. This referencing a fragment of Martian meteorite ALH 84001 found in 1984. ALH 84001 has fossils of what could be potential extinct microbial life, but 23 years later, the debate rages on. The 100%ers also point to the first reports of Viking 1 on Mars, reporting life is present and then rescinding the report later. The 100 Club also tackles the radiation problem by speculating that other forms of life can live under different conditions. Our limitations could be their source of life, or it could be they live underground or within a protective shield. They also can conceive of life that is not founded in DNA. All those arguments are relatively strong, but the 100% Club mostly back their intelligent life theory on the Miller-Urey experiment. Using science to disprove spontaneous generation, meaning that life just arose, also known as, pardon my Latin, omni vivum ex vivo, life only comes from life, the 1950s scientists Stanley Miller and Harold Urey set out to show that complex molecules of life could naturally arise from simple chemistry, and that life doesn't always have to come from life. The idea of a primordial soup of methane, hydrogen, and ammonia stimulated by the energy of lightning was considered by Darwin and more thoroughly considered by Alexander Oparin in the 1920s. The experiment found through a series of interactions the building blocks of life could be created in a test tube, resembling ancient Earth with sparks resembling lightning. Later experiments showed that the molecules of life can be formed in a variety of environments with different sources of energy. Building blocks of life can actually be found on meteorites, which implies building blocks could be all over the galaxy. Knowing life, any kind of life, found in our solar system would improve the potential existence of intelligent life. This Intelligent Life Club eagerly awaits an incredible find on Mars or one of the gas giant moons. Of course, there is frustration in the robots that search for that life. Robots are getting better, but it was once mentioned that a replica rover practicing in the desert on Earth that was teeming with life reported back to the scientists that there was no life to be found. Again, pointing out the shortcomings of our instruments. One could almost imagine a scorpion sitting on top of the robot as it reports back to the scientists. No life, no life. Summing it up, they believe that if you cannot decide on or find life close to home, how are you going to find life many light years away? The 100% Club is not worried about the burden of proof because they believe there is a preponderance of evidence to show that Earth's measuring instruments, although continuously improving, are inadequate. Our lack of scientific progress is boldly expressed in Alien Institute's video, "The Future Has Failed Us." Although there are many newer equations such as the Sharp-Kronen equation and the Seeger equation, along with multiple simulations to estimate the probability of intelligent life, nothing can compete with the classic and highly discussed Drake equation. The main reason it shines above the rest is because it was first and it did what it was designed to do. Prompt discussions on the idea of intelligent life, stimulate intellectual curiosity about the universe around us, and to promulgate energy invested into improving instrumentation. The Drake equation is expressed in the equation N equals R sub star times F sub P times N sub E times F sub L times F sub I times F sub C times L. I like to write it this way. Number of intelligent life forms that can communicate equals R sub star times F sub planets times N sub Earth-like times F sub life times F sub intelligent times F sub communicate times lifetime of a civilization, where, as we said before, N stands for the number of intelligent civilizations within our galaxy that can possibly communicate with Earth. R sub asterisk, or R sub star as I like to call it, stands for the average rate of star formation per year in our galaxy. Star formation is the process by which dense regions within molecular clouds collapse to form stars. Thanks to Hubble, NASA approximates 1.5 to 3 stars per year are created in our galaxy. F sub P represents the fraction of stars that have planets. Notice the letter F, which stands for fraction, will be a fraction that can be converted to a percentage that starts from 0 and can go all the way up to 100%. So 0% to 100%. Determining whether a star has planets uses a technique called microlensing, and with modern analysis, some studies show that as a rule, planets orbit stars. Formula-wise, you could look at F sub P as F sub P equals stars that have planets in the Milky Way divided by stars in the Milky Way. N sub E is defined as the average number of planets that might support life per star with planets. Some people view N sub E as a typical number of Earth-like planets orbiting a random particular star. Earth-like would imply capable of developing life. F sub L stands for the fraction of Earth-like planets that go on to develop life. Of course, this number is impossible to estimate, especially since the Earth is the only model that we have so far, presenting a really small sample size with degrees of freedom being 0. So we have the Earth and that's it to really to compare this to. Future Mars missions or Saturn moon missions could dramatically change estimates if life or past life is found. Another find that would improve the probability estimate for F sub L would be a non-DNA based form of life being discovered on Earth. Mathematically, we could look at F sub L as the probability that an Earth-like planet around a random star actually develops life. F sub I stands for the fraction of planets that developed life that have gone on to develop intelligent life. That's what the I stands for, intelligent life. As usual, without any real data, this probability is very hard to approximate. Arguments for the likelihood of intelligence on living planets range from many biologists pointing out that there are many animals on Earth, but only one animal has obtained so-called intelligence. Scientists with higher estimates claim that with the complexity of evolution, it can only lead to intelligence. It's also been stated that Neanderthal, a different species, developed intelligence to a high degree. Of course, if past life on Mars is found, it would reduce the probability for the intelligence factor, since that would be evidence toward basic life not becoming intelligent. F sub c. F sub c is defined as the fraction of the intelligent life on the living planets that communicate, that's the C, via a signal into space. It must also be considered that the planet is close enough for us to receive the signal. The civilization could be gone before the signal reaches us because it has so far to travel. Another consideration is that the civilization is capable of sending a signal, but they choose not to. The final parameter is L. We define L as the lifetime of the civilization at which they were sending a signal. Estimates of this go from 300 years to infinity. Some argue that the splitting of the atom could immediately end a civilization, and others argue that advanced minds and technology could lead to immortality. If the latter is the case, we could have been accumulating advanced civilizations from the beginning times of the galaxy. We will talk about the original and modern estimates in a minute, but briefly, I want to mention the great astronomer and astrophysicist, Dr. Frank Drake. He was one of the founders of SETI, the search for extraterrestrial life, and he mounted the first observational attempts at detecting alien communications. Like many of us, he wondered about life on other planets as a child. Later, his ideas about extraterrestrial life were reinforced by other scientists such as Otto Struve and Carl Sagan. So let's get to the chart and talk about the original estimates, current estimates, and then we'll leave it to you to create your own estimates. So looking at the chart, or what we could actually call a worksheet, since you have the ability to work the right-hand side and put in your guesstimates as to the probability that there's intelligent life out there in the Milky Way and that it has the ability to communicate with us, you'll be able to do that if you fill in the right-hand side. So for what we're going to do here is we're going to look at the parameters that we had just discussed earlier, and we're going to talk about the original estimates and the current average estimates. So R sub asterisk is the first one. I like to call it R sub star. That's the number of stars formed per year in the Milky Way. The original estimate was 1 star is formed in the Milky Way per year. The current microlensing and the current technologies has brought that up to 3, but that 1 from the original estimate plus the current, we get 1 plus 3. Take the average of that, we get 2. So that's the number that they're standing at currently. 2 stars per year in the Milky Way are being formed. Next parameter would be F sub p, the probability a star in the Milky Way has planets. The old estimate was 20% to 50%. That's the 0.2 to the 0.5. But again, with Hubble and current technologies, they're finding out that planets going around stars is not uncommon. So our solar system isn't really unique to the galaxy, and more likely than not the whole universe. It's a more common thing than we thought. So they have that one set at 99%. I guess they're being safe and not saying it's 100% chance. So the next parameter that we're going to look at here is N sub E. That's the number of Earth-like capable of developing life planets orbiting a random star in the Milky Way. So the old one was 1 to 5. They would look to say that there are 1 to 5. That was the original estimate, and we take the high number 5 plus the 3. I'm not exactly sure where they got those specific numbers, but that 4, the average ends up being between that 1 to 5 anyway. But it is on the higher side, 1 to 5. They're closer to 5 than they are to 1. So the modern or the current average estimate is 4. Okay, for the next parameter, F sub L, the probability that a random Earth-like planet capable of developing life in the Milky Way that has actually developed life. So you can see that the original estimates were really optimistic. They had it at 100% or at 1 in probability terms. And then what they do for the current estimate is they take the 0% club that we talked about. There's a 0% chance, and the 100% club, which is a 1 in probability, and they take the average of that. So that breaks down to an average of 50% chance that the F sub L, again, the probability that a random Earth-like planet in the Milky Way has actually developed life. They hold it now currently at 50%. The probability that a random Earth-like planet in the Milky Way that has developed life goes on to develop intelligent life, that's our F sub I, that's our next parameter. Again, they were optimistic. They said it was a sure thing. 1 is 100% in probability terms, and 0 is 0% in probability terms. So then on the, just to the right of that, the next column over, you see the 0 plus 1 divided by 2. We took the average of the 0% club and the 100% club, and we just split the difference and get 50%. So that's the current estimate, at least for the Drake equation today. Now, F sub C is, again, as we mentioned before, probability that a random Earth-like planet in the Milky Way that has developed intelligent life and is close enough and is willing to send a signal to communicate. So we look at our original versus our current. So the original was 10% to 20% that they would have the ability or that they would want to send communication. And again, they kind of split the difference over in the right side column, not your column, but the one in between that, and they go with a 0% chance that they would send information or send some kind of message to us, and 100%. So again, they split the difference at 50%, but it is higher than what it was before, because it was only 10 to 20%, and now that one's 50%. Whereas the F sub I and the other parameter, they split the difference. It was a 1, and now it went down to 50%. So each one of these parameters affects the final N, and it just depends on how much. As you may recall, we'll probably do some math videos on this down the road, but if you're multiplying fractions, it's getting smaller. If you're multiplying big numbers, such as N's and L's in this case, then obviously the ultimate number is going to get bigger. So L, we look at lifetime and the number of years of the civilization that has developed the ability to send a signal for communication, and the old estimate was 1,000 to 100 million years. So not exactly sure how they came up with that estimate historically. It'd be kind of interesting to talk to the people that came up with these numbers. Probably a panel of people, more likely than not, having a good time, having some fun and throwing their estimates and coming up with very general reasonings as to why those numbers would be the numbers. The current one goes up to 500 million. So that one seems to make a little more sense. If you really are an intelligent being and you haven't wiped yourself out, then maybe you are going to push to I wouldn't say immortality, but I would say that you would keep your civilization around for a very long time, or be able to move from one place to another where you could keep your species going, keep it alive. So how do we get these numbers? How do we get, you'll see this N down here, and of course that's the total number of intelligent life forms capable of communication with Earth. That's the number that we're looking for. That's the Drake equation. And the old estimate was 20 to 50 million. And as you can see now, the current estimate is 495 million. So that's a lot. That's just in our galaxy alone, by the way. So if you remember, it's in our galaxy, the Milky Way. It's not Andromeda Galaxy and all the other galaxies that are existent out there. So when we look at that, how do we get that number? What you do is you multiply each one of those numbers. So let's run down the column. I'm going to do, since if you were going to do the original estimate, you'd have to multiply all the left-hand side numbers, and then you'd have to do 2 and then multiply the right-hand side numbers. But since we only have one number in each box for the current average estimate, let's use that as our example. So what I would do in my calculator is I would take 2 times 0.99 times 4 times 0.5, as I keep going down the column, times 0.5 again, times 0.5 again, and times 500 million. Hit enter, and you should get 495 million. So again, you're running down the column and you're multiplying all the numbers in that column. So now if you've created your own estimates on the right hand side, what you do is just run down the column and multiply them all. Make sure you don't multiply, you don't get n yet. N is the product of all those entries, all those parameters that you entered. So that about does it for today. There may or may not be intelligent life in the galaxy. So don't forget to put your estimate of n in the comments below after multiplying your guesstimates in the right-hand column. As far as being a Type 3 civilization, that depends on you viewers as pioneers. We could grow linear with our technology, which would be okay. Worst case would be to grow logarithmically, but my hope, and I'm pretty sure it's the same hope for the whole crew here at Alien Institute, is that we grow exponentially, because the universe is too incredible not to be experienced by Earthlings.
Hi, this is Heidi von Helmholtz from Alien Institute. Don't forget to subscribe, strike the like, comment, and share.
You